Hi students. So under the subject algebra number theory, we are into unit 2 finite fields and polynomials. This is my second lecture. The topic for today will be roots of polynomials. So let's start. So before getting on to the definition of root of a polynomial, I want all of you to just recap over what is a polynomial is, right? In my previous lecture, I had explained what is a polynomial. So polynomial is some algebraic expression in one variable, right? So we can say x cube plus 3 is in a polynomial, x plus 2 is also a polynomial, etc. So what are the operations identified over there? Addition, subtraction and multiplication. Okay. Now what is not a polynomial? So whenever a variable carries negative powers and a variable carrying square root powers, that is whenever square root is present in the power or a negative power present in the power of the particular variable, then that will not be considered as a polynomial, right? So now you already know what is a constant polynomial, what is a zero polynomial, etc. So now let's see what is the root of a polynomial. So let R be a ring. I guess everybody remembers what is a ring. Ring is a set with two binary operations with identity 1, and let f of x is equal to a0 plus a1x plus a2x square plus so on plus an x bar n belongs to R of x. So here I see it's R of x and here it is mentioned as R. So now few might have a doubt. What is the difference between R and what is R of x? R is a ring, whereas R of x is a collection of polynomial rings. So try to understand the concept. So this will be a collection of all the polynomial rings. Now they are taking a polynomial. What is the degree of this polynomial? The highest power. The highest power of the polynomial is n. So now with the degree, f of x is greater than or equal to 1, they are saying. So necessarily we are going to take a particular polynomial mentioning its degree is greater than or equal to 1. So always take a polynomial greater than or equal to 1. Why so? Why they are mentioning it as greater than or equal to 1? Why can't it be equal? Why can't it be less than 1? Right? Why can't it be 0? There is another option. We cannot be negative. So why can't it be 0? So if I'm going to make a degree of a polynomial as 0, so what do I actually mean? I mean the power of that particular variable is 0. So if I write x to the power of 0, so later case I will arrive only at the constant. I don't have the variable. So to find a root of the polynomial, I need to have the variable inside. So for that, minimum one variable at least should be there. At least minimum x or more than that. That is why they are mentioning it as greater than or equal to 0. Unless and until there is no x, where will I go and substitute the value of x to find the root? So that arises as a question. So that's why the degree of f of x is greater than or equal to 0 is specified. Now we move on to the definition of root of a polynomial. An element a which belongs to R. So from R I'm going to take an element a. That I'm going to declare as a root of that particular polynomial f of x if I substitute that a inside the polynomial, I'll be getting a0 plus a1 into a plus a square into a square plus so on an to the power an, which is equal to 0. So actually what does it mean? If I substitute f of a, which means if I declare any variable that is a root, or sorry, any element in R, if I'm going to say it's a root, it should satisfy that particular equation. This you would already studied in your lower classes. So saying that how will I get the roots? For a quadratic equation, I start equating to 0. I factorize it. I get the roots. Right. Same thing you can do. For a square equation, for a cubic equation, you can go ahead. Right. But whereas for higher powers of a polynomial, it is going to be difficult for us. Right. Okay. So now let's continue. So now we'll have a theorem for it. So the theorem says that if f of x belongs to capital F of x, right, as degree n greater than or equal to 1, then prove that f of x has at most n roots in capital F. Right. What is capital F? Capital F is a field. So what is at most means it is maximum. Okay. So whenever you consider an equation, a polynomial with a degree greater than or equal to 1, then you say there are at most maximum only n roots will be available. So how are we going to prove this theorem? I guess we prove this theorem by mathematical induction. I hope everybody remembers what is mathematical induction is. You already studied this under discrete mathematics, right? So mathematical induction on the degree f of x. So how do I prove, how do I use mathematical induction? There are 3 steps. First, number 1, so we say we prove for n is equal to 1. Number 2, we assume n equal to k is true. And for the third one, n is equal to k plus 1 is to be proved. So 3 steps are there in your mathematical induction. So the same thing applications I'm applying here for this particular theorem. If f of x is degree 1, then f of x is equal to ax plus b. So you may wonder how this ax plus b came. It's just a normal representation of the polynomial. You already remember your polynomial starts with a0 plus a1x, etc. So which means a0 is replaced by b here and a1 is replaced by x for the convenience sake. Right. So now f of x is equal to x plus b, where a and b belongs to capital F and x a should not be necessarily not equal to 0. Here it's a very important condition, because if a is equal to 0, what will happen to this particular polynomial? This entire term, there won't be any x existing. Okay, with f of minus of a power minus 1, b is equal to 0. This is the function what I'm defining. F of x has at least one root in f. Okay, so if degree f of x is as 1, so what does it mean? It has at least one root in f. Right. Now what I'm doing is, if c1 and c2, I'm going to take two numbers or two elements, c1 and c2 are both roots. Then, so when I say they are root, what should happen? When I substitute f of c1, you should get 0. When I substitute f of c2, your answer should also be 0. That's why they are writing in this condition. AC1 plus B is equal to 0 is equal to AC2 plus B, which is equal to f of C2. Now, this you have already studied. Cancellation law in a ring. By cancellation law in a ring, AC1 plus B is equal to AC2 plus B, which implies, so right, you have two types of cancellation laws, right cancellation and left cancellation laws. So here you will be getting B and B will get cancelled. So AC1 is equal to AC2. Since f is a field and a is not equal to 0, so what happens? Again, you apply the cancellation law. So AC1 is equal to AC2, which implies C1 is equal to C2. So f of x has only one root in capital F. Right? So which means C1 and C2 both are the same. So I can say there is only one root here. So for 1 it is proved. Now assume the result is true for all the polynomials of the degree k greater than or equal to 1 in f of x, because it's mathematical induction process. So third step will be considering a polynomial f of x of degree k plus 1. If f of x has no roots in it, the theorem follows. Otherwise, let r belongs to capital F, f of r is equal to 0. By factor theorem, okay, factor theorem is just dividing a polynomial by another polynomial. Okay, so this is the divisor. Okay, now we are going to divide one polynomial by the other polynomial into the quotient, where g of x is degree k. Consequently, by the induction process, g of x is at most k roots in f and f of x is at most k plus 1 roots in capital F. Okay, so let's move on to the problem section now. So the first problem is finding the roots of a polynomial x square minus 2 over the real number capital R. So it is just observe, it is just a what type of equation it is? It is a quadratic equation. So it's just they haven't mentioned anything more complicated. They've just asked you to find the roots over the real number R, right? So since it's a quadratic equation, you can easily solve it. So given the polynomial x square minus 2 over r, you are equating that x square minus 2 is equal to 0. which implies from here you can say x square is equal to 2. So from here, what is the value of x? X is equal to plus or minus root 2. Now after getting the roots, right, you have to check whether these roots are lying inside R. What is R? It is a real number. So my root 2 and minus 2 definitely belongs in R. So therefore I declare that minus root 2 and plus root 2 are the roots in R. Right. So the extension of this problem, suppose if the problem is asked over Q, here it is asked over R, and here suppose if they are going to ask you over Q, then okay, what is the roots again? There won't be any change in the roots, but I have to check whether these roots lie or belong to Q. What is Q? Q is rational numbers. So I already told you this belongs to real. So this will not belong to Q. So therefore, under Q or over Q, there are no roots from this polynomial. Is that clear? So depending upon what it is specified, whether it is R or Z or Q, you got to discuss this. Okay. Suppose if this is discussed over C, complex numbers. Is this a complex number? It is not a complex number because there is no I over there. So definitely it does not belong to C. That is what my conclusion will be. Okay. So we'll move on to the next problem.